Hello everyone. Today is the 42nd day of Leetcode 75 challenge. Let's begin with the 42nd question. Question 450. Delete node in a BST. I will request you to read the question beforehand as I will deep dive into the PPT and explain it in simpler way. So you are given the root of a binary search tree. Okay. You are also given an integer value key. Your task is to search for the node in the BST whose value is equal to the key. And if such node is found, we just delete that node from the BST while maintaining the properties of the BST. Basically, they are trying to say that this is a binary. So they're saying that if you are asked to delete this particular node, so after deletion of this particular node, the property of the binary search tree should be maintained. So basically, if this node is deleted, this 9 should come up somewhere here like this and should follow the BST root. You can see that all the nodes in the left hand side are smaller than this particular node, and similarly, all the nodes are greater. Okay, so this is the structure you have to follow after, even if you delete any of the particular node. If the node is not present in the tree, we simply return original root because no deletion is needed there. The final output should be the root of the BST after the deletion. Updated if the node was deleted or unchanged if not found. So basically, if it is deleted, this is updated tree after deletion of the 8 number node, right? Or the node with the value 8. If the deletion is not there, we should return the root because nothing has been done, right? This is what our problem is asking. And the constraints, the number of nodes in the tree is in the range of 0 to 10 to the power 4. And node value could be from negative 10 to the power 5 to positive 10 to the power 5. And each node has a unique value. So there is no repeating value in any of the particular node. And the root is valid binary search tree. Okay, these two are the important things. And the key the key value which is asked which will be given to us for deleting into the BST would be from minus 10 to the power 5 to positive 10 to the power 5. Okay, so this is all about the constraints. I hope you understood the problem explanation. Now let's move to the next slide. Now let's understand the input output explanation. So here, if you could see, the key is given as to be 3. So this is the key, right? And suppose I have deleted this particular node. So what should happen? Let me draw the tree here first. Suppose this is the tree, right? And you have deleted this particular node. Now what should happen? Should 2 come here or should 4 come here? Suppose if you bring up the 2 there, suppose you thought I will bring 2 here, then 4 will come to the right side, correct? So is it a valid BST? Yes, it is a valid BST because in the left hand side everything should be smaller, right? So 2 is smaller than 5, right? And 4 is also smaller than 5 but greater than 2, right? So it is in the right side, it is correct. Or you could also have done this way, could have placed 4 here and 2 in the left hand side and let it be the same. Then also this structure is correct because all the values in the left hand side should be smaller, right? So it follows that particular rule. So this any of the two could be the output. It's your choice. And coming to this particular example, second one, here key is 0. And if you can see here, there is no 0 available in this particular given BA3. So we will just return the root itself. Okay, the exact tree will be returned. So this is what input output explanation was all about. Now let's move to the next slide. Before going into the further slide, let's understand what is a binary search tree. If you already know about binary search tree, you can skip this particular part and move forward. Otherwise, please stay in. So a binary search tree is a type of binary tree where every node, where all the values in the left subtree are less than the node's value. For example, let this be a binary tree. So this is a binary tree, for example. Okay, we know the concept of binary tree, but here if you can see, all the values in the right subtree are greater than the node's value. Okay, this property helps efficient searching, insertion, and deletion. So let me make you understand. Suppose this is a root node, and if you could observe in the left subtree of this particular node to the this particular node, and to the you could see that 8 is smaller than 10, 7 is smaller than 10, 9 is smaller than 10, right? Then if you come to this particular subtree, you could see this is smaller than the node, this is greater than the node. Fine. So what binary search tree says that for every node, the left subtree for that particular node will have all the values smaller that particular node to that particular node, and the value to the right subtree of that particular node would have all the values greater to that particular node. So if you could see, here is 10. All the values in the right subtree of this 10 we have greater than this 10, right? It is 12, 11, 13. So similarly, if you go to the most subtree, if you come to this particular subtree, you could see if taking 12 as the root node, you could see 11 is smaller than 12, but 13 is greater than 12. Similarly, if you go up, if you could see 10. 10 is smaller than 12, but 11 is greater than 10, but smaller than 12, but it is in the left subtree of 12, right? Similarly, in the left hand side also 8. 8 is there, and to the left it is 7, but to the right it is 9, but 9 is smaller than 10. So everything to the left subtree will be smaller than that particular node, and everything to the right subtree will be greater to the particular node. That is what a binary search tree is. And how it works, we start from the root node. We, for any operation, for insert, search, or delete, we compare the target value with the current node. So suppose a target value would have been given to you. Suppose it is 3 or 10, whatever, right? Let it be 8. Okay. If the value is smaller, we move to the left child. This helps in what? Let me tell you that. The value is smaller, we move to the left child. Suppose we have 8, right? If you're standing in the root node, you can easily check, okay, we have 8 to be searched and 8 is smaller than 10. So it is a knowledgeable thing that we don't have to go to the right subtree anymore. We will just be going to the left subtree for figuring out the value, because in the right, every value would be greater than 10, right? Which will be, of course, greater than the value 8. And when you come to the left subtree, you will be knowing, okay, we have the 8 here. So this is what we were searching for. Even though if the 8 was not present there, suppose it was 9, okay, to be searched. So here you would have checked, okay, since this is 8 and the given value is 9, you might have moved to the right subtree, excluding the left subtree traversal, and you might have moved to the only the right part, okay? And we repeat until the value is found. So this way the efficiency is much more. As time complexity in average case comes out to be log n, because we basically are dividing it by n by 2, okay, in every iteration. And worst time complexity could be O of n when tree becomes skew trees. And what is a skew tree? Skew tree is which does not have both the childs. So if this is a skew tree. So if you have to find, suppose you had to find 6 here, right? So you have to traverse complete tree to get that particular 6. So in worst case it becomes O of n. And space complexity becomes O of h, where h is the height of the tree for recursive operations. Okay, that is all. That is all about binary search tree here. Now, where binary search tree is used. So I have put down some of the problems where you could use binary search tree, which is fast searching, inserting, and deletion. Okay, use when you need efficient operations on dynamic sorted data sets. For example, search or insert value in binary search tree, Leetcode 700 and 701 questions. Okay, find the minimum and maximum values or the next larger or smaller element. You can use BST ordering to quickly find those values. Find in order successor or predecessor. These are the questions you could solve. And thirdly, finding LCA in a binary search tree, you could use this, and it makes the complexity much more efficient. Now, validate or serialize BST also, you could use the concept of binary search tree, verifying the integrity or saving the restoring tree structure. Find the k smallest or largest element. We can use in order traversal to get the sorted data for order statistics. Because if you know in order traversal, and when you do the in order traversal of a binary search tree, you always get a sorted order from in ascending form. Please keep that in mind. Always you get ascending order values when you traverse the binary search tree in order traversal. So this way you could find a k smallest element, k largest element, anything you want, right? And balance BST or guaranteed performance is basically using self-balancing BSTs to maintain log n time worst case, such as AVL or red black tree implementation. So these are the few of the implementations of the binary search tree you could go through to make your concept much more stronger and much more efficient. So I hope you understood the concept of binary search tree. Now let's move to the next slide. To understand what problem is asking, we should build up an intuition to the problem. Let's do it by understanding the goal first. Okay. So we are given the root of a binary search tree and a targeted value. Fine. Our objective, uh, our objective is to delete the node that has the value equal to the key while ensuring that BST structure remains valid. So we have the understanding of these two particular points. Now, if the node with the target value is not present in the tree, we just return the tree unchanged. Okay. These three things are directly given to the question and it is understandable to us. Now, what happens if we delete a node? Okay, let's think about that. The deletion behavior depends on the number of children the node has. Fine. No children. Simply remove the node. Okay. Suppose it does not have any children to it. So what we will do, we'll just directly delete it. Okay. No need to do any kind of change or something like that. If it has one child, suppose let's take this example itself. Suppose here this node has only one child. Okay. Since this node has to be deleted, we replace the node with its only child. So if this has to be deleted, we just replace it with it. Okay, it could be the right child or it could be the left child, but it has to be the one child itself. Okay. If it has two children, then what to do? And look for any one of the node which could be the predecessor or successor. Okay, and we can just replace it with that particular node. Okay, let's take another example. Let's say we have this. Okay, and let it be a longer tree. Suppose this has to be deleted, right? This node has to be deleted. Then what we could do? If this is something, all the nodes to this particular left side will be smaller to this, right? And right will be greater to this, correct? So what you can do is that if you delete this, you can delete it. We can bring this particular node here. Why? Because in the left hand side, if you know, suppose this is 10, this has to be some value which has to be less than 10. You are with me at that point, right? This has to be smaller than 10. Okay, or we could say that this is the greatest value. You could say no, not the greatest value. You could say that this is the value which will be greater after this particular node, right? So you could just replace this node with here. I will explain this in much better or much nicer example in the next slides. And you could just bring this particular node here, or you could just bring this particular node here. We will discuss about that, how we're gonna do that. Okay. Also, converting the BST into a sorted structure and rebuilding could solve this. It's unnecessary and inefficient. What does that mean is that in the brute force solution, so let's talk about the brute force solution. In brute force solution, what you could do is that suppose you are given a BST, right? You could just traverse the BST and you could look for the node to be deleted, okay? And what you did, you deleted that node, okay? Or secondly, you could just, converting the BST into a sorted structure and rebuild could solve this unnecessary or inefficient. Uh, or this could be inefficient and unnecessary. Reason being, suppose this is the BST, okay? You deleted this node, you have to delete this node. What you will do? You will traverse the complete BST, okay? And you will create a new tree. As soon as you get this node, you will just skip it. Okay, you will then directly take its children's and put it here. Okay, you could do that, but it is a no unnecessary work has to be done there. Another tree has to be created. Secondly, it becomes inefficient because you have to traverse the complete tree, and it will take O and plus O and time, and it will take some time. Okay, so we can take the example advantage of BST. So please keep in mind whenever a BST tree is given, before going to any of the solutions, just look at the properties of the BST first. Okay, if then go through the properties and think of something which relates the property. Okay, and take the advantage of the BST sorted nature to guide our search path directly toward the node. Okay, once the node is found, we rearrange the appropriate pointers to perform the deletion and reconnect the remaining tree correctly. So what we could do, instead of creating a new tree, we can try to find out the node which has to be deleted, and we could rearrange the appropriate pointers to perform the deletion and reconnect the remaining tree correctly. Basically, we could just restructure the tree without creating a new one. So I will explain this particular point, the two children point, which is the most important one in the upcoming slide. Okay. Now let's visualize the process. Okay, so I have drawn the tree. Now let's look at the visualization process. Okay. We start at the root and compare the key with the current node's value. Okay. Where that particular node exists. Suppose the val be, let it be 10. Okay, let it be 10. So So starting here, you will check as per the BST rules. Okay, 10 is less than 20. So it will of course exist in the left hand side of the tree or the left sub tree of the tree. Okay, here. Then you came here. Again, you will see that 10 is less than 15. Again, you have to go to the left hand side of the tree or the left sub tree, which is this one. Okay, great. Now you're standing at 10. Now you have two things to be done. Now, if you remove 10 from here, okay, let me remove 10. Of the 10 was 9 and right hand side was a 13. Now, what you could do is that you could either place 9 here, right, like this. If you place, you connect 15 with 9 in the left hand side, which is correct. And to the right side of the tree, left side is null, right sub tree could be 13. If you could see the pattern, it is correct, right? What you just did, you just took the left node of the tree and you just placed it here and you have taken you connected its child or the leaf part to the right subtree of the 10. Okay, and now it becomes a proper BST without any violation. Okay, one thing is that what if you don't want to do that? Then what you will do? You will say I will take 13 and I will connect. No, that is not possible, right? What you will do? You will come here in this particular part of the tree. Okay, 13, and you will go to the leftmost part. So if you go to the right subtree, okay, you went to the right, then you will go to the leftmost node in the complete tree. Okay, basically that will be the leaf node. Okay, so if you come to the right subtree and you go to the leftmost leaf node of that particular tree, you will reach here. Am I correct? Yes. Now you will say that I will connect the left hand side of this particular node to 9. Okay, and right side will be null, of course. So what will tree will look like? Let me draw it for you. If you remember, yeah. And you said that I will say that this 13 from where I started, I will take this tens right. Basically, this will get connected with the tens parents connectivity here. Okay. Now, if you could see 15 left hand side comes out to be 13, which is correct. 13 left hand side is 11, which is correct. And there is 9, that is also correct. And towards the 13 right, there is 14. So there is no violation, and we got the BST correctly after the deletion of the particular node. So you have checked that what we did nodes parent, okay, which is 15 in this case, left. In this case, it is left, right? Left, I will say left edge will be connected to the right of 10. Right of 10 is the right subtree of the 10. Okay. So you have seen here there are two ways to create the BST after the deletion of the particular node. Correct? One was the 9. Since you said I will take the you know in here also the same case. If you go to the left, if you take the left subtree, you will take the rightmost value, which will be the leaf. Okay. If suppose you came to the left, okay, and there is no rightmost, there is left only. You will take the left value. That is also correct. That is also not wrong. Correct? That is also not wrong. Because suppose if you had suppose 8 after 9, you might have taken this also, right? Then also will be no issue. Then you will do what? You will connect 8's right to this particular left of the right of the deletion of the node, and you will say that node's parent left edge will connect with 9. So this is also correct BST. So this is the important logic we have to remember, that if you choose the left subtree, you have to go to the rightmost leaf node. Okay, and it does not, if that does not exist, it becomes the rightmost leaf value, and you will check, since here there is no right node was there, right? So you took the left one. Okay, if the rightmost is not present, then you take the leftmost. Okay, and if you take the right subtree here, you go to the leftmost node, which is basically the leaf node, and you take that. And if that is not present, suppose if in this case if 11 was not present there, you might have taken 14, correct? Then also it have been correct, right? Then its left will have pointed to 9. Okay. And also remember, if you take the left subtree, here you have pointed the right node to the right subtree. And if you have taken the right subtree, you have pointed a left node to the left subtree. Am I correct? Yes, I'm correct. And this is the particular clarity of this particular question. That is what it is written here. If it matches the root, we call a helper function to handle the deletion logic. Helper function is basically finding out the node for doing the connectivity. If key is less than the current node, moving to the left child, and this is the BST logic itself. Yeah. So we continue this until we find the parent of the target node. Parent of the target node, as I said that parent node is necessary because parents left. Suppose this is the left case, right? It might have been that the value would have been in the right side of also, right? Then everything would be same. Everything would be same. Only this particular edge will be replaced, get replaced with this particular edge. So then it will be nodes right. Okay. If it has only one child, we return the child. That is the thing. If it has two children, we find the rightmost node. Here I've written one of the case. Okay, I've written here the rightmost node of the left subtree. Rightmost node of the left subtree, which is also called the in-order predecessor. And right for the leftmost node of the right subtree, it is called as the in-order successor. Fine. If you don't know about in-order predecessor or in-order successor, by chance, if you don't know anything about that, please go and read about it. It is just as simple as it can get. Called the in-order predecessor, which basically means that if you go to the right subtree, suppose this is the right subtree, and you take its left, you go to the left subtree, sorry, you go to the left subtree of this particular node, and you take the rightmost node, this, okay? For this particular left subtree, you take the rightmost node, and this becomes the in-order predecessor. And similarly, for the right subtree, you take the leftmost value or node that becomes the in-order successor. That's all. We attach the right subtree to this node's right. If you remember, if you take this particular left subtree, we attach the right subtree, which is this one. Let me clear. So tree, we were attaching this if you were taking the left subtree, we were attaching its right edge to the right subtree. Correct? If you are taking this, or vice versa, if you take the right subtree. Okay. We return the left child to take the place of deleted node. So after doing this, after this connectivity, return the left child. What does that means? Returning the left child, right? And this was the left child, and this was the right child. Left child was the 9, correct? So we will return this child to its parent node. Then only the connectivity will happen, right? As I explained earlier, then only the connectivity will happen. So this is what it is. So, and for this particular complete question, we use while loop to ensure iterative traversal, avoiding recursion overhead. So this is one of the thing to be considered. If we use while loop, the extra stack space would be neglected. Okay, but bit tricky one, but it was easy to understand and easy to explain, right? Now, how we can simulate this? This is important. What we can do is that we can store a reference to the original root. Example dummy. Because we are not supposed to modify the original root, because after deletion, especially important is the root itself gets deleted. Basically, suppose if you take the root itself and you don't take a dummy node, and if you have to delete the root, we will delete this node, right? Then what we will return? We won't be able to return anything. Since the question asks to return the root, so we have to store it in a dummy node and do the operations in the dummy node or dummy root so that the original root does not affect. After that, if the root node value matches the key, we delete it immediately using the left subtree function. And now here We will create a left subtree function. Now, left subtree function is basically here. Will this becomes the left subtree. Now, in this particular question, how I have solved is using the left subtree. Okay, you could use a right subtree also. Every joinings or the pointer joinings will be just vice versa of it. So I'm taking the left subtree. I will call this particular function. I will create a function so that we could do the connectivity here. Okay, if we don't get the node, otherwise we traverse the tree iteratively. This is the concept of BST itself. Nothing to explain here. Only the target is found as the left or right child, we pass it to the left subtree to handle a deletion and reconnect the subtree. So what happens? Suppose this node has to be deleted and we are standing in the root node. Okay. What we'll do, we'll create a left subtree function and we'll pass here root left. Okay, root left. In this case, root left because the node is in the left of this particular root. Okay. Why root left I'm passing here? Because this is the node to be deleted, correct? And this is the parent node. And if you remember, we have to know the parent node of the deleted node, okay, so that we can connect this particular node to the parent node itself. Okay, for that we pass the root left means standing here we are passing this node. Okay, now the left subtree function restructures the subtree after deletion. Now what we will do, after coming here we have sent this value in the left subtree, correct? Now we will create a function the rightmost. Before coming to the rightmost, we can come here. The node has no left child. Okay, this is the important one. Suppose if you are standing, this is the node to be deleted, and you have saved this node in the left subtree. Now suppose if it didn't had the left subtree, okay, suppose the left subtree was none of this particular node. What you will do? You will return the right child of this particular node because, for example, if you take, so you will return this child, right? So this will get connected with this particular node. Am I correct? Yes. Similarly, if the right child was not there, then you might have returned the left child. Okay. If both were not there, if both were not there, suppose if both were not there, we will just return. Okay. But if both are there, let's say we have both, right? Now what we will do? We will use the rightmost function to find the rightmost node in the left subtree. Okay. In this case, we are taking the left subtree. Please remember that. So what we will do in the rightmost function, we will pass the root left, which we passed here, root left's left, basically this, right? This we will pass. So how we will pass that? We will store this root left somewhere in the here. Like for example, node equals to root, okay, whatever you got from the function call here, and we pass this node left. Okay. Now this is a to this nodes right now in the left. What we'll do in the left subtree, we will call the rightmost node within this function, right? Tree. Okay. And here we will point root right. Basically, root right means we have passed this in the function, right? And its root right is this, correct? So that when we find the rightmost node, suppose we got the rightmost node here, let it be right. What we will do? We will point it node rights dot right, okay, to the right tree. This way, if you're standing here and it will say that right pointer will point to this particular node. This way, all the connection will get removed from here. Okay. And this left subtree will return this root left after that to this particular parent. Okay. If we will take the left node, that's not an issue. This node is used to preserve BST structure during two child deletion. So this is how we will try to simulate. I will explain this in the approach part much clearly. What I figured out is that The root node itself is the target. We need to handle its deletion carefully upfront. Suppose if this deleted, what we will do? We will just remove this. Now, this is done. To draw again. Now, one is greater, this part is greater, this part is smaller. So this part will get attached to this particular part, right? And this becomes a new tree. Am I correct? Yeah. So this is what is the same structure which will be followed from both of the functions which we taken earlier, the rightmost and the left subtree. When deleting a node with two children, we must replace it with either the rightmost node of the left subtree, which is in order predecessor, or the leftmost node of the right subtree, which is in order successor, depending on which subtree we choose to ensure this BST remains valid. Here, we have taken this particular one. Okay. When a node has only one child or no children, we simply bypass it and return the existing child. If no children, we simplify the restructure. That's the thing. Suppose if there is no left children, we return the right, and there is no right, we return the left. This is the things which you figure out after solving the particular problem. I hope you understood the intuition explanation. It was a bit long and bit a complex one, but I tried to simplify it as much as possible. Now let's move to the next slide. Now, since you got the intuition of the problem, let's look into the approach how we're going to solve it. Step one, always handle base case and direct the deletion. What is this? The root is none itself. We return none, right? The BST is empty, so we don't have to do anything. Basically, if root is none, just return. Nothing to do. Or the root val, if it equals to the key. If you can recall, I talked about the rightmost function and the left subtree function, correct? And before going to that, if something was in the middle, suppose if the deletion node is in the middle, what we were doing, we were using a BST property. If the val is less than the node, we go to the left. If val is greater than the node, we go to the right. Right? We were doing all this stuff, correct? This is a BST property to search a particular value. But what happens if the root itself is the node which has to be deleted? We'll directly call the left subtree function. Okay, but that will help us. This particular nodes get deleted. Okay, and as per our left subtree function, we'll connect its right here, and our new tree will become like this. Okay, deleted is the root. Since the root may be replaced, we must handle this before any traversal begins. Okay. Step two is prepare for iterative traversal. We store the original root in a variable like dummy. We will have a dummy variable which will have the root so that we don't hamper the original given tree. Okay. If you delete a node deeper in the tree, the original root does not change. We return dummy. But if the root itself is deleted, we already handled that above and never reach this part. This is basically if this case happens, the root is to be deleted, root node, then we directly delete the original tree given to us. Or rather, otherwise, we take the dummy, put the root node intact, and do the deletion. Begin iterating from the root to locate the node with value key. Okay, and this is we do the traversal of the BST here. In step 3, traverse and delete the targeted nodes. We use a while loop to traverse down the tree while root or dummy, whatever. Okay, while till the time they exist. At each step, we check if key is less than root value, we go left. If root left exists, matches the key. Suppose this matches the key. We are not standing in the deletion, the node to be deleted. Okay, we are just standing in the root and we're checking if the left part, left node of that particular root is to be deleted or not. If it is, what we do, we call root left. Okay, the root left for this particular call will be equal to left subtree's root left. If you remember, we're passing the root left of the parent node, which is basically this, to the left subtree function to delete it. Because we pass root left, so that left subtree can return the new subtree that should take its place. And similarly, if the root val key is greater than root val, we go to the right. Basically, if there is a right subtree and this has to be deleted, then same structure will happen, just it will be root right. Okay. And why we are passing root left or root right in the function? We're telling the helper function or the left subtree function which exact subtree child node needs to be deleted, and we use return node to reconnect the parent to the modified child subtree. Basically, we're telling the function that, hey, the function which has to be deleted, or so the node which has to be deleted is this, right? So I'm passing this to the left subtree function. Now what do? You go and find the rightmost node, okay? And for this particular node, you check the right subtree, okay, and store it somewhere. And you point this particular node to here so that my connectivity with these two particular nodes gets removed, okay? And later return this to the left subtree, okay? This is what we will be doing. Now in step 4, how deletion works in the left subtree, okay? So this is the tree. If the node has no left child, suppose this is the node to be deleted and it does not have any left child, left child, we will return the right child and vice versa. Okay, nothing to do anymore in that case. This handles the simple 0 or 1 child deletion cases cleanly, which is bypass the deleted node. That's all. Since suppose if there is no left child only, that means this is the child or this is the node. Okay, how long this node could be? Okay, we don't need to care. Since there is no left child for it, we'll just return it, okay? And the parent will have this particular node connect to it. That's why we check it in the beginning itself. Using the rightmost node function, having the root left in that, is happy. Suppose this is the root node and this is to be deleted, okay? So what we are passing in left subtree? This node's left, correct? So in left subtree we have this, okay? And in the rightmost function, we will have this root left value. And in the rightmost function, what we will try to do, we will try to go as much right as possible. And if it does not exist, we take the next left value. This node is in order predecessor basically. It is the next largest value. Please read this line. It is the next largest value smaller than the node to be deleted, which fits the BST rule. Basically, it is the next, if this gets deleted, this becomes the next largest value smaller than the node to be deleted, but and also smaller than the right children or the right subtree. Okay, because if something this is 12 and suppose this is 10 and this is 9, correct? So 9 is less than 12, right? That's the case. Then we do right digit dot right, which is equal to root right. This is basically, so this right has to be connected with this particular left sub or right subtree of the deleted node. Okay, then what you will do? Then you will create a variable. Suppose here I have created right node. Okay, there we will place root right. This values right, which is this, right? And when you find this rightmost node, you will just point this rightmost node right edge to this variable right node. This way you get the connectivity. We move the right subtree of the node being deleted under the in order predecessor. This ensures all greater nodes still lie on the right side of the predecessor. Okay, this happens. Finally, we return the root left. Then this was the root in the left subtree, and we return the root left. Okay, so this gets automatically removed from the complete tree, and we get a complete BST back. The left subtree now fully includes both in-order predecessor and the former right subtree, if you can see in the figure, and becomes the replacement of the deleted node. Right? I think now it should be clear to you. And in final step 5, we just return the result. After the deletion, we return the dummy. That's all, which holds the new updated BST. I hope you understood the approach explanation. Now let's move to the next slide. So this is the base case. If root is none, return none. If you remember, I talked about if the root itself is the value to be deleted, we just directly call the helper function, or we could call it as left subtree function. This one, okay, directly. No need to traverse them. Otherwise, we place this root in a dummy node and we play all the game with this particular dummy node. Okay, if the left key is less than the root value, this is the normal BST properties. If you could check if the root left exists, And root left's value is equal to the key. If you remember, this is the parent node, okay? And we're telling the parent node's left value is equal to the key. If it is, then root left should have the left subtree function will be called with the root left value, which is a node to be deleted. Okay. And after that, we get the value from the left subtree here. If you remember these cases, if left is null, return right. If right is null, return left. Otherwise, if both are not null, just the right node should be, we figure out the right node from the rightmost function. We pass the root left here. Okay. We get the right node here from here. Okay. If we got this part, then what we do? Right node dot right, which we got, we will point it to the roots right, which we passed here, right? The root value, we point it to its right subtree, and we return the root left, right? This is simple explanation of the code, which we have already discussed previously. Now, the time complexity for this particular problem comes out to be O of h. H is the height here. Reason being, if you can recall, we are just jumping on the tree from top to bottom and just going through the height wise, or you could say level wise into the tree. Okay. And space complexity comes up to be O of 1 because we are using iterative solution rather than recursion and no extra space has been used. So I hope you understood the code explanation. Now let's move to the next slide. Now since we have the understanding of the code, let's look at the dry run of the example. Let me draw this tree first. Okay. Okay, let's begin the dry run. I've also brought the code here for your clear understanding. Okay. Here you could see if root is none. So we return none. So root is not none here, right? So skip it. Neither the root value is equals to the key. Here key is 3. So we take the dummy node and place the root there. Okay. And while root is not null, what we do? If key is less than the root value, it's 3 and we have 5. And 3 of course is less than 5. So what we have to do? We have to come to the left. But before that, we check if roots left. If roots left is exist and roots left value is equal to the key. So its value is 3 and it is equal to the key, right? So this is true. So what we do? We point root left here, okay? And the left subtree function, we pass root left, which is 3. So this is the left subtree function here, and we have 3 here. Okay, we have passed 3. Now, root left is none? No. Root right is none? No. Root right node is a new pointer which will have rightmost function called with root left. So this is the root, okay, and its left is 2, correct? So what you do? You pass 2 here. So in rightmost function, you have 2. So while root right exists, root equals to root right. So you come here and you stand in this particular node. Nothing to go more, right? So you place yourself here. Then we return the root here from here. So you return what? You return 2 from here. Okay. So in this particular right node, you get 2 as the return value. Okay. If I extend the tree, if there could have been 6 here and 5 here, then it might have written 6. Okay, for your understanding. If there might have been 6 here, then it will have written 6. Okay, great. Now, right node, right. So since you got 2, okay, this two's root right, this part will belong to roots right. So what was roots right if you remember? Since this is the root in the left subtree, then it's right. Then this value is right will be equals to the root right. So it will be basically equals to 4, or you could say this will point to 4, and this will get removed. Okay, then you return root left, then you return roots left, which was this, right? So you return this back. Then here was the left subtree in the roots left, and if you remember in this particular function, root left was this. Okay, so this gets this particular 2 back. Okay, and this points to this, and this gets removed from the scene. So what our tree becomes after writing it properly, and we return the dummy, and which returns this particular tree. So if you can check, all the value to the left of 5 are smaller than 5. All the value greater than all the value in the right subtree to the node to the, if you can check, all the value to the left of 5 are smaller. All the value to the right of 2 are greater. Okay. All the value to the right of 5 are greater than 5. Similarly, it follows the same. So we have got a valid BST after deletion of the node. I would suggest going back and understanding the intuition, the approach, the code, and the BST logic if you don't know. After that, do a dry run by yourself in 2, 3 examples, and I'm pretty sure you will understand both the solution and the thought process behind it. Now let's move to the next slide. Now, since you're familiar with the problem and the solution, let's move to the lead code and code the solution. Let's start by checking if root is none. Then just return none. If root value itself is the key, we just return and call the self dot left sub tree function with passing is root as the method. Okay, dummy will we will create dummy otherwise with the root. Then while root exists, if key is less than root dot val, we check if root dot left exists and root dot left dot val. So by chance if it is equals to the key. Okay, if it is equals to the key, what we'll do, we'll connect root left edge with the self dot left sub tree return value. It will be root dot left. Okay, we'll pass left here and we'll break out after that. Otherwise, we will go to the root dot left. Okay, we'll iterate more. That means we will iterate more, or we will go much more deeper in the left hand side following the BST rules. And otherwise, root dot right and root dot right dot value that is equals to the key. Then root dot right will have the self dot left sub tree with root dot right passed in it. Okay. Remember, when passing root left and root left, you will have nice idea about it. And root right, why? Because we found the node in the right hand side. Suppose 5 was the root and found the 6 node to be deleted. Right? That's why we did that. And after that, we just break. Else, if that is not the case, root equals to, we go to the much more brighter side. Okay. And we just return the dummy after that. Great. Now let's code the left subtree. Def left subtree will have self, it will have self, then it will have tree node with it. To make it much more clear, it will return a tree node. Okay, and this will be a root. If root dot left is none, return root dot right. If root dot right is none, return root dot left. Correct. Otherwise, you create a right node and call the self dot rightmost function and pass the root left right node right will then point to root dot right subtree and we will return the right node from here. We will return the root left. Okay, that's then if we got make the right most. Okay, cell while root right exists, we go to root dot right, and after that we just return the root what we got. Okay, let's try submitting for the sample test cases. We got an error here. Okay, so I can, okay, let's finally submit the solution. We successfully submitted our solution. Now code of the problem is available in my GitHub repository. You can find the link in the description. Thank you everyone.